This surface represents one of the biggest challenges in surface analysis. It's a surface that's been worn on the right-hand side, but remains unworn on the left-hand side, and it's indicative of a typical problem we encounter, and it's a problem of measuring the amount of wear in a surface when it hasn't worn all the way through into a scar. So we're not going to be able to measure the volume, say, of a hole in the surface. Instead, we need to explore how much of the peak material has been worn away. Now, this is another frontier in tribology that we've yet to explore. In the study of tribology, of friction, lubrication, and wear, we tend to accelerate our testing. We'll add extra force or temperature or pressure to create that deep wear scar so we can measure something. But this is more indicative of the real world. This is how a piston ring might slide in a cylinder bore, and we have a worn region and an unworn region. In some cases, we might have measured a surface before and after testing, and they don't live on the same data set, but we have this sense or this indication of what unworn looks like and what worn looks like. So we're going to use OmniSurf3D's new Microwear analysis tool to explore this. So let's start with putting a cylinder in this surface as a reference and an 8-micron robust short filter. So we've already applied those, but I'll show you how the data looks after doing so. So our filtered surface clearly shows that the surface has been worn. We can see how the peaks have been removed. What we can do with the Microwear tool is we can save an unworn surface. So what I would do is I would crop in here and grab a region of data in the unworn area. Now this could have been another measurement altogether, but I have now a sample of what the unworn surface looks like. Now I've filtered it, processed it, leveled it, and all those things, so we can go out to Export Surface and to the filtered surface option. We're going to export that. We will save this. I'll save it onto the desktop and we'll call it before, for example. I've got an old file there. We'll replace it. So I've now saved what the surface looked like before testing. And again, this could have come from an entirely different measurement. But let's now move down to the after test area of this surface. And we can see that's a bit more plateaued. And with that surface active, I can go to our new tool. Under Wear Analysis, we have Microwear Analysis. And there's that filtered surface we were just looking at. And I can now load an unworn reference surface. I put that on the desktop as before. And we can see the two surfaces together. Now they're currently plotted where they're both plotted relative to 0. So they're both averaged or they're both zeroed. This is not how they sat in reality. In reality, the valleys were kind of lined up, not the 0 points. And the material probability curve gives us a great visual on what's happening. We can see the unworn surface in gray that matches kind of the gray surface over here, and a black plot for the worn surface. And I can grab the black plot and slide it up and down, and as I do so, you can see the surfaces on the left sliding up and down. But right here where my cursor is sitting is a region where they have similar statistics. Those lines kind of match up. And in this zone right here is where statistically the valleys are lined up. Even though we measured in two different areas, or it could be two entirely different surfaces, these two data sets have similar valleys, and if we can latch those valleys together, we can report the amount of material lost in the peaks. In fact, that material lost in the peaks is represented by this area between the two curves over here, and we can report a number, 0.69 cubic microns per square micron of area. So we can drag this around and line up those regions. Something else we could do is just tell the software, look in this zone. Right here seems to be the statistical zone of our worn surface, and auto compute, meaning line up the worn with the unworn. And as we do that, this zone is now latched together and we get 0.68 cubic microns per micron squared. So this tool is going to give us a much more reliable tool because it's a volume, not just a height, which is noisy, but the actual material volume lost during wear at a microscopic level. Now, as we improve materials, we improve lubrication, we improve our sliding surface systems, the ability to measure wear at a finer and finer scale is going to become more and more important. And we have exactly the tool for this in OmniSurf3D. To check this out with your own surfaces, download the trial copy of OmniSurf3D today, or for any conversations or questions you might have on this topic, reach out to us at digitalmetrology.com. We love talking about this, and this is an exciting development we'd love to share with you.